Today we're going to look at section 2.1, which is trigonometric functions of acute angles. Now what's nice about acute angles is, first off, they're all in quadrant what? 1. And in quadrant 1, all of the trig functions are positive, so that's a plus. Another nice thing about acute angles is that you can form right triangles from them. So we can also stop looking all the time in a rotational sense on the xy plane and start looking now at an actual triangle, a standalone triangle not in the xy plane. So this looks really busy, so I'm going to talk you through it and try to make it kind of condensed for you. We are going to redefine the 6 trig functions inside a triangle as opposed to an xy plane. So what I have up here are the 6 alternate definitions of the trig functions. So these are the right triangle-based definitions, sometimes called the alternate definitions. You should know these from geometry. All right, so we're going to start with sine, cosine, and tangent because those are our primary. And notice that sine of any angle, we're just going to call it capital A, is defined as y over r inside the xy plane. But when you're in a standalone triangle that isn't in the coordinate plane, you can define it as the opposite side divided by the hypotenuse. Cosine of an angle inside a right triangle can be defined as the adjacent side, the side that is adjacent to that angle divided by the hypotenuse. And tangent of angle A inside of a right triangle can be defined as the opposite side divided by the adjacent side. And then, of course, you can find your reciprocals from there. Most of you learned this as SOHCAHTOA. I believe you did anyway. SOHCAHTOA. Problem with SOHCAHTOA is for a long time I couldn't spell it, so it didn't do me a lot of good. I finally learned how. I also learned this. I just remembered that it's in order as it is on your calculator. Sine first, then cosine, then tangent. And I just learned Oscar had a heap of apples. So that works as well. To me, it's easier if I write them this way. And this may be what you want to jot down. Sine of an angle inside a right triangle equals O over H. So that's sine. Cosine of an angle inside of a right triangle is adjacent over hypotenuse, or A over H. And finally, tangent of an angle inside a right triangle is the opposite side divided by the adjacent side. And once you have the 3 primary, you can do the reciprocals just off to the side if you need them. So cosecant is the reciprocal of sine, so that would be hypotenuse over opposite. Secant is the reciprocal of cosine, so that would be hypotenuse over adjacent. And then tangent, cotangent. Cotangent is the reciprocal of tangent. So that would be adjacent over opposite. It's important to note that when you're not in the xy plane, when you're in a right triangle, and guys, the trig functions are only functional for right triangles, just like the Pythagorean theorem. It's important to note that it is a relative thing. It depends on the angle you are looking from. For example, if I look right here at angle A in this drawing, and I imagine which of the 3 sides is opposite from angle A. Opposite means the one it doesn't touch. So that's the y side. So y and opposite in this case are the same. Then the hypotenuse and r would always be the same. And adjacent is the one that touches the angle but is not the hypotenuse. So in that case, x would be the adjacent. However, if you look instead from this angle, and on the xy plane we never do that, but in a triangle situation sometimes we do. If I look instead from angle B, which side is opposite? X, right. So you have to be really careful because it is a relative thing. Let's pause here and see if anybody has any questions. So for our first example, we have a triangle here. We call it triangle ABC. I'm going to go ahead and point out to you that if you remember from geometry, angles in a triangle are usually named with capital letters. And so in a right triangle, we always or almost always, we let the right angle be capital C. So that's pretty standard throughout this entire book. So here we have this right triangle, and we want to find just the sine, cosine, and tangent values for both of the non-right angles A and B. So the first thing we want to do is find sine, cosine, and tangent of angle A. So we want to turn our attention to angle A, which is this angle here. So you want to imagine that you're looking from that angle. Now we define sine as the opposite side length divided by the hypotenuse. So in this case, which of the sides is opposite of angle A? 7 over the hypotenuse, which is 25. So the hypotenuse doesn't change depending on which angle you're looking from, only the adjacent and hypotenuse. The adjacent and opposite switch out. Now the cosine of angle A is defined as the adjacent over the hypotenuse, which in this case is 24 over 25. Remember that the adjacent side is the one that is one of the two that it touches, but not the hypotenuse, and you can always keep it straight there. And finally, tangent. Tangent is the only primary trig function that does not involve the hypotenuse. It only involves the legs. It is the opposite leg divided by the adjacent leg, which in this case is 7 divided by 24. So that's the sine, cosine, and tangent of angle A. None of them will reduce, so we're finished, and there are no radicals in the denominator. They're as simple as we can get. Now let's come over here, and let's find the sine, cosine, and tangent, but this time of angle B. And let's see what they look like. All right. So in this case, the opposite over the hypotenuse, if I look from angle B, so we will go up here and shift our focus to angle B. The opposite is what? 24. The hypotenuse is still 25. Uh-oh. I think I'm in the wrong spot. Here we go. Let's do it out to the side. 24 over 25. The cosine is the adjacent over the hypotenuse, which in this case is 7 or 25? 7 is adjacent and 25 is the hypotenuse, so 7 over 25. And finally, the tangent is opposite divided by adjacent, so 24 over 7. A couple of things I would like to point out, not something you need to worry about yet, okay, but something, trig is all about relationships, and here's a neat one that I can point out. If you're looking from either of the two non-right angles in a triangle, and you find the sine of one, it will always be equal to the cosine of the other, and vice versa. Also, the tangents will be reciprocals of each other. And that's true. It's not something you need to concern yourself with, but it is always a true statement.
So the tangent of A is always reciprocal of tangent of B.
It's always the reciprocal tangent of B.
And sine
So
of
I guess
A.
that basically means tangent of A would be the same as cotangent of B, right?
And sine of A is equal to cosine of B.
Right. These two are equal here. And those are the ones people start to kind of like get used to and use more and more through physics or whatnot. At this point, we want to talk a little bit about what we call the co-function identities. You do not have to memorize them unless you absolutely want to. What they do is they tell us when the rare occasion is that a trig function can equal its cofunction. So there's only a specific time when sine can equal cosine. It's not unique. It can happen, more than one different type of angle, but it is very specific. When sine can equal cosine, tangent can equal cotangent, or secant can equal cosecant. And that is only true when one of the angles is A and the other is 90 minus A. In other words, it's only true that cofunctions are equal only when their angles are complementary. So for example, sine of 40 would equal cosine of 50. Sine of 20 would equal cosine of 70. So that's something you'll need to know for the remainder of trig. So let's jot that down here. If you don't want to memorize the 6, we can just memorize that cofunctions are equal only when their angles are complementary. What's another way of saying that? That they add to what? 90 degrees. So they add to 90 degrees. So that's how you solve them, that's how you check them. Alright, so let's look at examples where we could actually use the cofunction identities or the statement that we've learned about them. These instructions say write each function in terms of its cofunction. So I'm going to start you off with a trigonometric function, and you're going to tell me the cofunction and angle that it's equal to. So let's start with cosine of 52 degrees. What is the cofunction of cosine? Sine. Yeah, not the reciprocal, the cofunction. So if it has a co, you drop it. If it doesn't, you just add it. That's how you get your cofunction. So we know that cosine and sine are cofunctions, but in order for them to be equal, what does this second angle have to be? Has to be whatever adds to 90. So in other words, it has to be whatever 90 minus 52 is, because they have to be complementary, and that is 38. So most of you can figure that out without really doing anything. Yeah? Okay. The tangent of 71, the cofunction is cotangent, also happens to be the reciprocal. And in order for those two things to be equal, the angles have to add to 90, so that would make that one 19 degrees. If you're not sure, just subtract it from 90. 90 minus 71 is equal to the cotangent of 19 degrees. Did I do the arithmetic right on that? Is that right? Yeah. 90 degrees. And finally, the secant of 24 is equivalent to the cosecant of, anyone?
66.
66, yeah. Which is, we get that from saying, okay, 90 minus 66, 90 minus 24 is 66. Be sure you put your angle mark on, so you have your units there too. Those are degrees, so you have to put a degree symbol on. So that's the first type of example we could do using those. Any questions about that? Pretty easy? And how do you check them? Does anyone know? You're holding a calculator. You can put it in degree mode and make sure you get it right, right? And so we'll be talking about very soon how to enter secant, cosecant, and cotangent into the calculator. But you could also just check to make sure that the two angles add to 90. Here's the other thing, and for some reason, this bothers students more. I give you two cofunctions that are already equal, and I ask you to solve for the variable in the angle. So for the first one, we know that cosine of theta plus 4 degrees is equal to sine of 3 theta plus 2 degrees. That's called a trigonometric equation. We have two trig functions set equal to each other, and the variable is part of the angle. Does anybody have any ideas for what I could do to solve that? I'll give you a hint. It has nothing to do with trig. It does. It has a little bit to do with geometry, and just about that one statement we've memorized. The only way for those two things to be true is if their angles add to what? 90. So does it make sense to you guys that you just ignore the trig functions? If you see cosine and sine equal to each other, you ignore the trig functions. You take their individual angles and you add them together and set them equal to 90. So we know that theta plus 4 plus 3 theta plus 2 will have to equal 90. And you just kind of have to know to do that. That's something you have to memorize, you have to train yourself to be on the lookout for. Theta is treated just like an x, so theta plus 3 theta is 4 theta. 4 plus 2 is 6, and that equals 90 degrees. So 4 theta is equal to 84 degrees, and that means theta is equal to 21 degrees. The nice thing about that one is that you can plug back in and check it. If I plug back in, this tells me that cosine of 21 plus 4, so 25, is equal to sine of 3 times 21, which is 63, plus 2, which is 65. So you could check that in your calculator, or you could just check to make sure that the angles add together. I recommend checking it anytime you can. I'm going to pause for a second and let you finish the last one and see if you can figure it out. For the second one, we have tangent of 2 theta minus 18 degrees is equal to cotangent of theta plus 18 degrees. Because tangent and cotangent are co-functions, that means that their angles have to be complementary. So if I want to solve that equation, I can just ignore the tangent and cotangent and take their angles and add them together and set them equal to 90. The 18's cancel, so we're left with 3 theta is equal to 90, and theta equals 30 degrees. And you should always kind of plug back in and check it, just to make sure that they are indeed complementary later. And once we learn how to type the trig functions into the calculator, I think we might even talk about that in the next couple of examples, then you could also actually check it when you plug it back in to make sure the actual values are equal, not just that the angles add to 90. All right, that's a good time to take a break.